Under the dense, smoky haze of an airport tarmac, an Airbus A320 prepares for takeoff. As the engines roar to life, the aircraft's high-bypass turbofan engines spin up to their full power. Just a few moments later, an unsuspecting flock of birds flutter in the sky, unaware of the colossal force they are about to encounter. Suddenly, a bird strikes the leading edge of the engine's fan blade, a moment that could spell disaster. Yet, astonishingly, the engine continues to function flawlessly, the enormous machine unaffected. How is it that these massive engines can consume a bird and still rise high into the sky? Why do jet engines deliberately take such risks with avian life? This question reveals hidden layers of engineering designed to ensure the safety and reliability of air travel. The stakes are high. Passenger safety depends not only on engineering precision but on the variability of an airliner to withstand such impacts. In a world rarely seen, a remarkable intersection of physics, design, and resilience awaits us, an exploration into why jet engines are built not only to endure but to adapt. To understand how these engines survive bird strikes, we first have to delve into the mechanics of a high-bypass turbofan engine. A standard commercial jet engine operates on the principle of thrust generation, where air is drawn in, compressed, and ignited to create propulsion. High-bypass turbofans, which are the preferred choice for commercial flights, have large fans at the front that draw in air. Approximately 85% of the thrust is produced by this bypassed air, allowing for greater fuel efficiency and quieter operation. Now, consider this. When a bird weighing roughly 4 pounds collides with a jet engine at takeoff thrust, approximately 32,000 pounds of thrust in an A320, the kinetic energy involved is substantial. The speed of that bird as it meets the engine is the equivalent of a small projectile hurtling toward a critical engine component. In physics terms, the momentum of the bird can be calculated using the formula, momentum equals mass times velocity. For a 4-pound bird flying at a velocity of about 100 miles per hour, the momentum reaches over 200 pounds per foot per second, a force that is simply staggering. However, bird strikes have been a known risk since the dawn of aviation, leading to stringent safety requirements mandated by the Federal Aviation Administration. FAA certification requires that high-bypass turbofan engines ingest this 4-pound bird at full thrust without losing power. This is no small feat. The design specifications call for unique geometry in the fan blade assembly, ensuring that the blades can redirect the energy from an impact rather than simply absorbing it. The fan blade geometry is critical in determining how the engine will respond. Rather than being purely flat, fan blades are designed with an airfoil shape. This design not only enhances aerodynamics during the operation but also acts strategically during an impact. The curvature enables the blades to slice through the air, while its robust leading edge, often reinforced with titanium or other durable materials, helps to deflect bird impacts. This leading-edge armor serves as a strategic checkpoint, preventing damage from transferring deeper into the engine core. The containment of blade fragments, should a blade break under the stress of a bird strike, is another crucial part of the design. High-bypass turbofan engines employ a fan case designed to contain any debris resulting from a strike. This robust external casing acts much like a protective shell, holding fractured pieces and ensuring they do not penetrate the engine or, worse, the aircraft cabin. The fan case might appear mundane, yet it is conversely the linchpin of safety in this intricate system. To illustrate the effectiveness of this design, we can look at the case of the Airbus A321 that encountered a bird strike shortly after takeoff from New York in 2009. In this instance, the aircraft struck a flock of birds, yet the high-bypass turbofan engines absorbed the impact. Their intricate design with leading-edge armor and robust fan casing ensured the plane could land safely with no injuries to passengers or crew. Importantly, this isn't a shield against all strikes. Engineers note that the geometry and materials are tuned for the average bird strike. In practice, larger bird strikes can still cause significant damage, and this is where the field of aviation engineering constantly evolves. Design teams are perpetually refining engine structures to account for various bird species and their behaviors, utilizing predictive modeling and extensive testing to evaluate durability against potential impacts. Now, one might think that the larger the engine, the better it can handle such strikes. This assumption carries a flaw. Some might imagine that heavier components could withstand impacts more effectively, but heavier machinery can amplify forces differently, potentially leading to catastrophic failures. Instead, the combination of light, strong materials and a carefully optimized geometry in the blades yields resilience without adding excess weight. In fact, the concept of utilizing advanced composite materials in newer engine designs is reflective of current engineering trends. Such materials can provide not only durability but also a significant reduction in overall engine weight, promoting fuel efficiency. Let's pause for a moment. Which of these machines would you least want to be standing next to? A massive ship anchored in a harbor, a towering crane lifting steel beams, or a powerful jet engine devouring a bird mid-flight? The choice may tell you a lot about your own understanding of mechanical safety and strength. Upon delving deeper into these design considerations, we find a noteworthy misconception. Many assume that engineers aim for engines to absorb impacts from birds entirely. However, the reality diverges from this belief. Engineers do not seek merely to absorb shock, they design these engines to redirect and manage energy effectively. This is the actual trick. It's not that a bird can be obliterated on impact but rather that the impact is internalized, redirected around sensitive engine components. What all this showcases is a remarkable blend of safety, physics, and engineering insight, a collective effort to produce machines that interact dynamically with their environment. Consider the fan blades not simply as harsh surfaces, but as intricate elements designed to engage intelligently with forces they encounter. Finally, as we reflect on the series of engineering marvels lying beneath the surface of aviation, we recognize the extraordinary feats these machines accomplish daily. Bird strikes, initially perceived as catastrophic events to be avoided, are instead integral to the design philosophy of jet engines. They instructively remind us that even in the engineering world, unexpected challenges can become opportunities for refinement. Through the lens of these massive machines, we begin to appreciate an intricate tapestry of technology that tirelessly works to ensure our safety. From precise calculation of force and momentum to innovative material advancements, every element is a nod to fundamental principles of engineering that govern and safeguard air travel. The machines that move the modern world are stranger than they look. Subscribe, and we will take apart the next giant together. As we continue to dig deeper into the fascinating world of high-bypass turbofan engines and their ability to withstand bird strikes, it is essential to explore the broader context of aviation safety systems. The engineering marvels inside an engine are complemented by other designs in aircraft. One critical area is the monitoring systems that track engine performance and detect anomalies. This capability becomes especially vital when a bird strike occurs. Modern jets are equipped with advanced engine monitoring systems that continuously assess performance parameters such as temperature, vibration, and airflow. For instance, if an abnormal vibration is detected following a bird strike, alerts are generated to inform pilots about potential issues even before the aircraft lands. The ability to monitor and analyze data in real time provides layers of safety that bolster the robustness of the engine design. It's interesting to note that the first known bird strike incident was recorded back in 2006 when a jet struck a flock of birds during takeoff in the early days of commercial aviation. Engineers learned the importance of acknowledging such encounters and began developing better protocols and technologies to ensure that aircraft could handle these occurrences. As a result, FAA regulations became increasingly stringent, and continuous cycles of improvement led to the aviation industry becoming one of the safest modes of transportation today. Aircraft designers take into account a multitude of factors when creating engines, including not only the possibility of bird strikes but also the various sizes of birds. For example, the FAA's certification test involves releasing a 4-pound bird at a speed of approximately 100 miles per hour into operating engines. This standard reflects encounters with a wide range of bird species, including those like Canada geese, which can weigh up to 12 pounds. This multitude of variables underscores the importance of collaborative research between engineers, ornithologists, and meteorologists, constantly refining how they approach bird strike risks. Consider the sheer magnitude of the challenge. The mid-sized Canada Goose, with a wingspan of up to 6 feet, and a weight as high as 12 pounds is not just a simple target. The geometry of the geese as they fly and move within flocks creates unique dynamics that can influence aircraft's approach to safety. For instance, engineers have developed birdstrike testing programs that incorporate lifelike simulations, allowing researchers to observe and analyze strikes in settings that mimic real flight conditions. Such improvements not only enhance designs but encourage a culture of proactive risk management. In addition, safety measures extend to the field of air traffic management, where protocols are enacted to guide aircraft away from known bird habitats. For example, several airports around the world employ avian radar systems that monitor bird activity around runways and provide real-time alerts to pilots and ground control. This technology can play a critical role in preventing potential incidents before takeoff, further contributing to the mission of comprehensive safety in aviation. While the focus of today's discussion centers on the engines, another aspect worth tackling is the methodologies used by engineers to analyze the consequences of bird strikes. This is achieved through advanced computational fluid dynamics simulations that model the airflow patterns around airplane engines. These simulations can predict how airflow changes when an object strikes the fan blades, providing insight into the subsequent forces acting on the engine structures. Engineers utilize such models to optimize designs, ensuring that airflow is managed both in normal operations and during unexpected encounters. In the case of failed bird strikes, engineers recognize that not all scenarios can be accounted for in design. Take, for example, the engine failure of a McDonnell Douglas MD-80 aircraft in 1995 after a bird strike. The failure occurred due to an exponentially larger bird impacting the engine at critical takeoff acceleration, forcing the pilots to execute an emergency landing shortly after takeoff. The event led to new analyses and improvements in engine design concerning safety measures, increasing investments in bird strike testing and certification. Upon further inspection of the engine components, we find that modern turbofan engines often utilize shear pins or similar structural devices within the fan assembly. These pins are designed to fracture under extreme levels of stress, allowing both the fan assembly and engine core to separate cleanly, ultimately preventing catastrophic engine failure. This clever design decision reveals another layer of resilience that allows specific components to endure severe impacts while guiding management of the overall structure. Moreover, the materials used in manufacturing these components play a significant role. Most modern engines utilize titanium and advanced composites because of their strength-to-weight ratio and extraordinary resistance to fatigue. For instance, the General Electric GEnx engine, which powers the Boeing 787 Dreamliner, employs an innovative blend of composites and titanium alloys. These materials contribute to the overall efficiency of the jet, while also meeting stringent safety standards. One cannot overlook the element of long-term testing protocols that enhance reliability. Modern engineering drives design teams to create engines that not only meet regulatory requirements but exceed them. For example, the Pratt & Whitney GTF engine revolutionized design with a geared turbofan architecture, allowing for even greater operational efficiency. The testing included multiple strike simulations that confirmed its ability to withstand impacts while delivering outstanding thrust and performance. Now, let's examine the false belief that larger engines are inherently safer. Many people assume that a bigger engine can endure impacts better due to heavier construction. However, bigger engines can exacerbate problems due to the greater momentum they create. Larger, heavier parts can lead to more severe failures if they disintegrate upon impact. Engineers believe that lighter, optimized components with advanced materials can provide both the needed durability and safety without courting the issues associated with excessive mass. Furthermore, the maintenance protocols that aircraft undergo play an indispensable role in their resilience. Once an engine has experienced a strike, routine inspections are critical in ensuring that no latent issues arise. Technicians conduct thorough visual inspections as well as deeper forensic analyses of engine components post-flight. These inspections reveal wear and tear, while necessary adjustments and replacements are performed. Every layer of safety and engineering detail contributes to an overarching philosophy: aviation is about preparation and resilience. This philosophy is evident in other components of aircraft systems, such as the brakes. Aircraft brakes contain oversized discs forged from lightweight, heat-resistant materials like carbon-carbon composites, ensuring quick and responsive stopping power. Importantly, engineers ensure that these braking systems can handle emergency situations irrespective of normal operational parameters, providing redundancy and security beyond what we typically perceive. As we take a step back and reflect on how aviation technology has continually progressed, we appreciate the invisible threads of design that connect all of these elements. Each advancement seems to prompt another question, driving innovation to embrace what we once considered impossible. Every step forward not only protects passengers but opens doors to future technologies. While we've explored how jet engines withstand bird strikes, we also celebrate how they reflect humanity's ingenuity and resilience. We break boundaries and set unprecedented standards, transforming past challenges into engines of innovation that forever alter the landscape of aviation. As we conclude our exploration, we emerge richer in understanding, armed with a new respect for the technology behind avian encounters. We bear witness to a world where potential threats are acknowledged and systematically solved through engineering excellence.